display settings.
Yes.
All right.
Okay, so thank you for the introduction, and hi everyone. My name is Nikunj, and I'm a final year undergraduate student at the Indian Institute of Technology, Roorkee. And I'm here to present our work that recently came out as a product of collaboration with Professor Doug and his team at the Jülich Supercomputing Center, and Professor Satish and us at the Indian Institute of Technology at Roorkee. So this past spring, we worked on evaluating asynchronous many-task programming models on ARM-based platforms with HPX as our AMT of choice. So before moving on to the benchmark and results, let's look back at what HPX and AMTs are. Now, AMTs differ from the conventional SVMT models in a few ways. So firstly, an AMT defines work in form of tasks, and these tasks are linked as a DAG. So these links then depend upon any data and or control constraints that are put up by the user. Secondly, an AMT is responsible for extracting as much or little parallelism. So an application programmer simply defines the task and their constraints. Well, finer control to the parallelism is also available if the programmer requires. And finally, these tasks are run as separate threads that we like to call as the lightweight threads. And this is because they have very low overheads. The runtime handles the synchronization of these tasks, and it also maintains the schedules and schedules them. So since the scheduler deals with the task management, load balancing of these tasks is handled by the runtime itself. Now, HPX is one of the examples of an AMT and is based on the ParalleX Execution model. The ParalleX Execution model addresses the critical bottlenecks of the exascale HPC systems like starvation, latency, overheads, and contention. I have explained how it handles all these issues in the paper. So if one wants to look into details, they can always refer to the paper. As for HPX, HPX is the first open source implementation of this ParalleX model, and it allows for wait-free asynchronous parallel programming. It is composed of 4 main components. The AGAS handles the global view of the tasks. The network layer uses the information to dispatch these tasks on other nodes. The threading subsystem is composed of lightweight threads and abstractions around it. And finally, the LCOS are responsible for the synchronization that happens within the runtime. In our evaluations, we make use of the Roofline model, so I thought I should include them in the presentation as well. So the Roofline model gives a performance estimate using the processor's peak performance that I call CP here, and the system's memory bandwidth, or the IO bandwidth, denoted by BW. Now, using these values, we can plot a graph similar to the figure that figure 3, and depending upon the application, it can either be memory bound or it can be compute bound. Now, given a kernel with an arithmetic intensity AI, we can find the peak attainable performance using the formula attainable performance equals minimum of the computational performance and the arithmetic intensity multiplied by the bandwidth.
I apologize for the interruption, but myself and several others appear to still be on the title slide. We're not seeing your slides advance.
Yeah.
Would you mind pausing the presentation and then resuming the screen share? Basically turn it off and turn it on again. Let's see if that helps.
Yes, so let me try that again.
Great, I see benchmarks now. Could you try advancing a slide and let's see if it updates? That's great, thanks. Yes, it seems to be working now. Thank you.
Nice. So should I go through it again, or?
No, that's fine. Take it from wherever you feel comfortable. Thank you.
Okay, so as I was telling, the AMT model first, how it differs from the SVMT model, and this is how a DAG looks for an AMT in general. Then we came to the HPX and ParalleX execution model. I talked about what the ParalleX execution model is, and what HBX is, and how and its four main components. And then I was talking about the Roofline model. So the Roofline model tells about the expected peak performances that can be expected from a benchmark. And I was talking about the memory bound or compute bound performances that can be expected. And now moving on to the benchmarks, we benchmark two different stencil codes. So for the first one, we have the 1D Stencil Distributed, and it's a fully distributed 1D heat equation solver. And instead of reporting the execution time for the kernel or the kernel performance in, let's say, milli-lattice site updates per second, we thought that we should just report the total execution time and check how it actually scales on a distributed scale. For the performance of the kernel, we implemented another stencil code that is a 2D stencil based on the Jacobi method. And since we were talking about the kernel performances, we thought that let's just extend the application to support explicit vectorization. This allowed us to observe auto vectorization performances from the current day compilers and compared it with the explicit vectorization that we have in our application. So from our application design and the available cache sizes, we assume an arithmetic intensity of 1 by 12 lattice site update per byte for floats, and for doubles 1 by 24. And as we'll see later, the larger cache sizes can allow for even better arithmetic intensity, and we may just see higher arithmetic intensity for the benchmark. For the explicit vectorization, we use NSIMD. As Quentin said, it allows for portable vectorization, and this is what helps us in analyzing the performances on different architecture without actually changing the codes and without actually having to introduce different vector intrinsics for the code. And for parallelization, we use the HPX parallel for each loop. And we have our custom grid container. So instead of the array or the vector that you may see in general in C++, we implemented a custom grid class that we use to hide all sorts of data layout that we have for the explicit vectorization. For the system setup, we test on 3 ARM processors, namely the first one being the Fujitsu FX1000 based A64FX, the Marvell Thunder X2, and the HiSilicon Hi1660. And we compare it with the Intel Xeon E5 2660 version 3. For the compiler, we stuck to the GNU GCC compiler. The decision was more forced and actually not chosen. You see, the ARM compilers implement SVE types by using special keyword that is sizeless struct. Adding it allows runtime type and length analysis, which allows for SVE type portability, which helps in adding SVE length at the runtime. But at the same time, if we implement an abstraction using SVE types, we are required to define the struct as sizeless struct as well. And this is bad for us because we use custom grid class and STL features, and all of HPX is standard C++. And if we were to add SVE types and use NSIMD with it, then it would actually not be able to compile. So we had to stick with GCC because only GCC allows us to pass SVE length at the compile time. And while this reduces the portability, but it does allow us to compile the code. For the memory bandwidth, we run a stream copy benchmark for the usage in generating the Roofline model. The array size is 120 million, which is large enough to not fit in the cache sizes. For the results, for 1D stencil, we see that the benchmark is able to scale almost linearly. For strong scaling and for weak scaling results, we see that there is no visible increase in the execution times. For the HiSilicon processor, however, we see that it does not scale well. On a closer inspection, we observed that the very poor network performance results were the reason behind the very high latencies. And since we could not hide these latencies, the scaling effect is very poor, and it can be easily seen in the weak scaling as well. The figure 5 shows the stream copy results, and with the array size of 120 million. For almost all of them, the stream results are similar to what people expect. However, for the A64FX, we see a bit lower, around about 600 gigabytes per second, compared to what the Fujitsu claims at 800 gigabytes per second. On a closer inspection, we found out that higher memory bandwidth results are possible if we use the right allocate method that Vinay talked about. And it is possible, but we do not add this technique, and we use the 600 gigabytes per second result because we cannot add similar techniques to the stencil code. And since we are trying to propound the differences in expected performance arising from the stream results and our observed results, we thought that it is better not to add it to the code itself and use the standard stream result that we got from the GCC compiler. For the 2D stencil with the Intel E5 and the HiSilicon Hi1660, the plots show the observed results along with the expected peak that was calculated using the stream results and the principles of Roofline Model. For Xeon E5, we see that about 10 to 15% better results were observed when using vectorization. The vectorized results can also be considered optimal as they are similar to expected peak performances. Other than that, we see that the auto vectorization isn't doing really well, as the explicit vectorization has 40% less instructions. But at the same time, we see that the explicit vectorization has 75% more cache misses, and that is the reason why the explicit vectorization code isn't exactly significantly faster than the auto vectorized code, even though it has 40% less instructions. For the HiSilicon model, we see significant gains in performances. Looking at the performance counters, we found that auto vectorization and explicit vectorization had similar instruction counts, but with a 20% difference in cache misses, with explicit vectorization having 20% less number of cache misses. We believe the remaining differences is observed due to the stall cycles, the hardware backend stall cycles, so to say. So we believe this because we see something very similar with the Marvell ThunderX2 as well. And we could not conclude this, however, because the HiSilicon chipset does not support the hardware stall counters. Other than that, performances, we noticed that performances decrease from 32 to 40 cores and from 48 to 56 cores. This is because one NUMA domain is only partially saturated while others are fully saturated. This creates a bottleneck, and the partially saturated domain becomes the critical path, decreasing performance overall. For ThunderX2 and A64FX, we saw something very interesting. The results we observed were significantly higher than we expected. This is because due to the very large cache sizes, we see a decrease in memory transfers, increasing our arithmetic intensity and performances. So as we claimed in a previous slide that we assume 3 memory transfers, we just realized that okay, we can get even less memory transfers if the cache sizes are large enough. And that is exactly what we're seeing with the A64FX and the Marvell ThunderX2. So for A64FX, we see similar performances for vectorized and auto vectorized codes. There isn't really much of a difference. One thing of interest is that the auto vectorized code with the A64FX has 20% less instructions. That is, the explicit vectorization that we added had more instructions than the auto vectorization that was done by GCC. But the performances of explicit vectorization was slightly more because of the less number of backend stalls of about 60%, resulting in a slightly better performance overall. For the ThunderX2, however, we see significant gains, as very similar to the HiSilicon Hi1660. So on a closer inspection, we found out that the hardware stall cycles were responsible for this improvement, and hence why we said that the remaining differences with the Hi1660 might be just a result of less number of hardware stall cycles. So we still do not understand why the doubles or the 100x2 scales the way it does. Uh, at the lower core count, if we see it behaves as if 3 memory transfers are occurring, while at higher core counts, let's say above 16 cores, it all of a sudden switches as if thinking that the cache sizes is bigger, or we don't quite understand what exactly happens there, and it's more of an open question at the moment. But overall, we see that for the floats with 100x2, it was significantly better, and the cache sizes does help. So concluding, we found that the porting is mostly straightforward for both for the ARM ecosystem, but there should be further work that is required to integrate custom containers, such as containers like our grid class, to work with the sizeless struct, the keyword sizeless struct. And in general, we found that the performances with ARM are as good or better than the x86. With 1D Stencil results, we saw that it is very easy to distribute and scale on ARM ecosystem as well. And the scaling issue with the HiSilicon processor is mostly due to the poor network performances and not exactly because of the processor itself. And at the same time, we also saw that the large cache sizes within the Marvell 100x2 and A64FX allows for about 50% more performances just because of an increased arithmetic intensity. And it was mainly because of the inherent cache blocking effects that we were seeing within the 2D stencil. Other than that, we see that there are only minimal gains if we are trying to auto-vectorize a memory-bound code for the Xeon E5 and the A64FX. However, we see significant gains with the 100x2 and the HiSilicon processor. So thank you. And if we have time, I'd like to take some questions.
Thanks very much. Very interesting talk. Here is, have you looked at the 3D stencil code?
I have not. We were initially going to do only 2D stencil, but then we realized that it's nice to see distributed scaling, so we went for the 1D stencil. We could have gone for the 3D stencil code, yes, but we did not.
All right, I think I have a question. So there's a lot of interesting data points here, different comparisons across different platforms, a lot of interesting things. But considering that ParalleX is a different execution model, what do you think is the most important performance characteristic? For instance, I wouldn't expect x86 versus ARM to have much impact in terms of the instruction set alone. I would expect something like HBM or the wide cache lines of A64FX to have a greater impact than the fact of it being an ARM architecture. So given all the different architectures you considered, what do you think is the principal component for performance impact as far as ParalleX is concerned?
Overall, what we think really came down to the instruction set itself and the vectorization. The implementation for the ParalleX model is such that it does not really it does abstract most of the architectural dependencies away. And since HPX is implemented with the standard C++, most of its characteristic is exactly similar to what one can expect using standard C++ libraries. So the general characteristics come down basically to the vectorization available and the hardware cache sizes and similar principles.
All right, thank you. Another question. The peak performance of the platforms is quite different, especially considering something like a HI-1616 to an A64FX. Do you have a graph for the Roofline to compare these different processors to give a better sense of that performance gap?
We did not plot the Roofline model. I mean, we did plot the Roofline model, but we do not have it in the paper. But we use this formula for the attainable performances that is defined with the Roofline model. We just assume arithmetic intensity based on the cache sizes at first, and then we calculated bandwidth using the stream benchmark, and using these, we calculate the expected performances that we see over here. So the expected performance, let's say for the Intel Xeon E5 here, is about 7.5 giga lattice site updates per second. So I believe according to this, if we see the memory bandwidth here, it's about 110. So assuming 1 by 12, it should be somewhere about here as well. So that's how we calculate the expected peak performances. We did plot the Roofline model for the analysis, like when we were actually writing the paper, but we did not plot them in the paper or in the presentation.
Thank you. Great. Okay, I think that's all the questions we have.